Hello everyone, welcome back to the second class of the quantum mechanics. In the first class we talked about the basic introduction of how weird the quantum world is, isn't it? So let's begin with some basic concepts of quantum mechanics. Before we delve into it, we should know how this quantum mechanics originated. So the first thing is, we know about atoms, nucleus, isn't it? Let's say this is a nucleus and these are the electrons. But how these conceptions began? So the first theory was given by JJ Thompson. Okay, and he gave the plum pudding model. So what did Thomson say? Thomson said that suppose this is a cake and this cake is positively charged. This cake, this is positively charged. And on this cake there are electrons which are negatively charged. So suppose this black thing, this is the cake, and these blue things are cherries. So this is how he imagined the model. Thomson suggested that atom is a positively charged solid sphere. Okay, he said atom is a positively charged solid sphere. Okay, and electrons are embedded. Electrons are negatively charged and they are embedded on it. And this way, the atom is neutral. Atom doesn't have any charge. So this is the general idea of how JJ Thompson explained how atoms look like. So that idea of that there are fundamental particles called atoms goes back to very old centuries. The atomic theory was first given by Greeks. There were some ancient Indian philosophies too, but the scientific discoveries began with the idea given by Thomson in 1898. Okay, thereafter we have Rutherford's model. You must have read this in preliminary classes. What did Rutherford do? Rutherford looked for a thin sheet of gold. Okay, and then he bombarded alpha particles on it. He found that 90% of the alpha particles just passed through without any reflection and all. And this way he postulated that most of the space of the atom is vacuum or empty. Okay, and some particles got deviated, and this he said this must be the nucleus and this must be positive charged. Okay, so this was the generalized idea of how Rutherford's model was given. Because he shooted alpha particles on it which are positively charged, it got repelled, so the nucleus must be the positive charged. Okay, most of the alpha particles pass through. So this is the Rutherford's model. Well, there were some drawbacks in Rutherford's model. What were the drawbacks and limitations? So let's see limitations of Rutherford's model. What were the limitations? See, the first limitation is Rutherford said that the atom has nucleus which has the concentrated mass and it is densely positively charged. Around it there are electrons which revolve around it. Okay, which revolve around it in circular motion. So if we look at some Newtonian mechanics, anything which revolves around circular motion must have a centripetal force. Okay, centripetal force. So Rutherford postulated that the electrostatic force between a electron and a proton must be fulfilling the task of the centripetal force, which is mv square divided by r. So here what it will be 1 by 4 pi epsilon naught. Let's say the nucleus has Ze and the electron is E, where Z is equal to the atomic number. Okay, let's not delve into it. And r is the radius is equal to mv square by r, which gives us with equation of what? mv square is equal to Z square by 4 pi epsilon naught into r. This is one equation. So Rutherford postulated that since the electrons are moving in circular path, the centripetal force here is been provided by the electrostatic force. Okay, so the movement of electrons around the nucleus was necessary in Rutherford's model, and this would mean if the electrons were at rest, they would fall into the nucleus because of Coulomb's attraction. Okay, since the electrons are moving in circular path, the centripetal force has been provided by the electrostatic force or the Coulomb's force. Okay. Rutherford's model explains the charge neutrality. He says that in an atom, it has got plenty of empty space. These are empty space. This is the nucleus, and this is the electron. So it also says that because the positive charge nucleus is so heavy that when an atom gets energy from heating or otherwise, the particle gets hardly affected. That's why we see only electrons are coming out. We never see protons coming out. Protons never come out. Only electrons come out. Why? Because it has got so much empty space and the proton has the concentric mass. Hence, whenever we put any heat or any external energy, only the electrons come out. So during this time also, there was a particular effect called photoelectric effect, and it was discovered accidentally by Hertz. Okay. So what did it say? So let's say this is a metal surface, polished metal surface, and on it comes sunlight or light, and this causes an electron to eject from it. This is the gross idea of photoelectric effect. It says that there is needed a critical or threshold frequency, which is needed. In yesterday's class we saw h is equal to h nu, where nu is the frequency. So there is needed a threshold frequency which is required to evict the electron from the polished metal surface. Okay. He also said that since electrons are moving out, so this will lead to a current, and this current was called as photoelectric current. Photoelectric current. And this electron which comes out was called as photoelectron. So this was the whole idea of photoelectric effect. Right now we discussed that the critical frequency, critical or threshold frequency, okay, let's call it mu O, is such a way that whatever frequency we get is higher than mu O, okay, then there is photocurrent. So polished metal surface emits electrons. These are called as photoelectrons. So magnitude of photoelectric current is directly proportional to intensity of light. Okay. But energy of photoelectrons are independent of intensity of light. Okay. So this was further explained by Einstein, and in this way he emphasized on the particle nature of the light. So Einstein says light is composed of quanta, which he called as photons. Photons were called later on, but Einstein in his original paper called it quanta, with energy E is equal to h nu. Okay, this h is called as Planck's constant, which comes from the derivations of Max Planck. Okay, constant. So this h was already in use to explain the black body radiation. We are not going deep into it, just know the basic facts. Okay, so Max Planck came with this mathematical idea where he comes with a constant called as Planck's constant. He named upon his name, and he was puzzled by himself also why this idea is working in a strange way. He too didn't understand at that time. It was further explained by Albert Einstein, where he says that light is coming and an electron is being emitted. So there was the general idea that how much energy would it require to emit this one electron. Let's call it half mv square is equal to E nu. This is the frequency, Planck's energy, minus work function. So this is half mv square is equal to h nu, where nu is greater than the threshold frequency, minus w. So this was the explanation given by Einstein. Okay. So we got the basic idea. We started with how Thomson explained an atom looks like, then how Rutherford explained the atom. We also looked about the limitations of the Rutherford's model. Okay. And then we looked at photoelectric effect. Now let's talk about a peculiar feature called hydrogen spectra. Hydrogen spectra. Suppose this is an atom. This is an hydrogen atom and it is being heated. When it is being heated, what do we see? When anything is heated, we see radiation coming out. These are electromagnetic radiation. Okay. When an atom is heated, it emits energy in the form of electromagnetic radiation. And this radiation may consist of various components of various wavelengths. Okay. But when we observed it experimentally, we found that whenever hydrogen gas is being heated in a sealed tube, it emits peculiar or certain waves which are being repeated. Okay. We found this most striking feature that only some sharply defined discrete wavelengths exist in the emitted radiation. And this was the big question. It comes around 656.3 nanometer to 486.1 nanometer. Why only these two wavelengths? This was a great question back then. When an hydrogen atom was heated, it was seen that it emits electromagnetic radiation. But whenever this radiation happened, it comes with some peculiar discrete wavelengths, and which comes around repeatedly 656 or 800, 486. Okay, so why this type of things are happening? So there was a school teacher called Balmer. Okay, and he comes with the idea that this wavelength is equal to 386.56 by m square minus 4 into m square, where m is 3, 4, 5, 6. He just comes up randomly with this with the equation. He doesn't know why this happens. Later on, it was seen that 1 by lambda is equal to r by n square minus m square, where r is the Rydberg's constant. Okay, and this Rydberg is the guy who comes with this equation. Okay, so 1 by lambda is equal to r into 1 minus n square minus m square, where m and n are integers and m is greater than n. How this thing happens, we will describe later on. Just for now, just look at the equation. Okay, so this was a peculiar phenomena. We didn't know why this wavelength, certain wavelengths are coming. Hence, some guys tried to get an equation and they come up with this random equation. Okay, for now, this is what we know. Let's talk about some other difficulties of Rutherford's model. Other difficulties of Rutherford's model. Just now we see in Rutherford's model there is a proton and there is an electron moving around the nucleus in a circular path. It says the electron is moving in circular path, hence the Coulomb's force acting between them acts as the centripetal force. But we know whenever there is an accelerating body, there should be electromagnetic radiation. Electromagnetic radiation, according to Maxwell's equation. Maxwell's equation of electromagnetism says that whenever there is an accelerating body, it should emit electromagnetic waves, which means the revolving electron should therefore always emit. Therefore, the revolving electron should always emit radiation, isn't it? But if the radiation is continuously being emitted, energy is spent. Suppose there is an electron which is being revolving around the nucleus and it's spreading electromagnetic waves, and if constantly it emits electromagnetic waves, the energy of the electron will decrease, and suddenly what will happen? Eventually, if this is the nucleus, electron started moving and then it got dampened and dampened and dampened, and suddenly it will collapse into the nucleus. But we see this doesn't happen. So Rutherford's model couldn't explain why electron doesn't collapse into the nucleus. Okay, Maxwell's equation says that any accelerated electron must continuously emit electromagnetic radiation. But if the radiation is continuously emitted, the energy spent on the radius should gradually decrease and electron should finally fall into the proton. But we see this doesn't happen. So this was the phenomena which the Rutherford's model couldn't explain. Okay, we see that electron never collapses into the nucleus. And to solve this, here comes Niels Bohr with Bohr's model, and which is the most famous model, and we will discuss it today. So what does Niels Bohr say? Bohr comes up with four postulates. First postulate is that electron revolves around the nucleus in circular orbits. His second postulate is orbit of electron can have only special certain radius. He also says these electrons don't emit any energy as Maxwell's equation. Maxwell says that if there is an accelerated particle, it would emit electromagnetic waves, but Bohr says in certain values of radius, electron doesn't emit any energy, and he called them as stationary orbits. Okay. Then he says in his third postulate that energy of the atom has a definite value. Energy of the atom has a definite value in these stationary orbits. Stationary orbits. So let's say this is the nucleus and this is a stationary orbit where an electron is moving. So Bohr says even if the electron is moving in these stationary orbits, there is a particular energy E. And when an electron is moving in this stationary orbit, it doesn't emit any wavelength, any electromagnetic radiation. So this is the main postulate of Bohr. And in his fourth postulate, which is famously called as quantization of Bohr, where he says that in stationary orbits, angular momentum, which is denoted as L, of an electron, Bohr says that in stationary orbits, the angular momentum of an electron around the nucleus comes around L is equal to nh by 2 pi, where n is an integer. Okay, so these are the four postulates of Bohr. Let's look at them once again. First postulate is if this is the nucleus, electron revolves around the nucleus in circular orbits. Second, the orbit can have specific radius. Let's call this radius r, and these specific radius are called as stationary orbits where the electron doesn't emit any energy, and these electrons have specific values of these stationary orbits. Okay, and fourth is quantization of angular momentum. So these were the four postulates of Bohr, and according to these postulates, Bohr explains hydrogen atom. We just saw a few minutes ago the enigma of hydrogen atom, that hydrogen atom emits wavelengths of certain wavelengths which couldn't be explained, and then some random physicist and a random maths teacher comes up with an equation and which explains why the wavelengths come in certain values. But now Niels Bohr will explain how the whole thing is happening. So let's understand it very clearly. So this is the nucleus having a single proton, and this is the stationary orbit of hydrogen atom where there is an electron E and it is moving. So Bohr says let's calculate the force between them. So force will be equal to 1 by 4 pi epsilon naught. Let's have the protons charge as Ze and electron as E. So Ze into E, and we have R, so R square as a radius. Let's call it equation 1. And we have mv square by R as the centripetal force, so let's call it 2. If we equate them, we will come up with the value of Z is square divided by 4 pi epsilon naught into mv square. Okay, using 1 and 2, we come up with radius, and this is equation number 3. This is the basis. Okay, now just now we have seen that Bohr's fourth postulate says L is equal to nh by 2 pi, where L is the angular momentum, which is also written as mvr. So we will write mvr is equal to nh by 2 pi. Okay, and just now we have seen we have got the new value of R. Okay, so we can put it here. We can write mv into Z E square divided by 4 pi epsilon naught into mv square is equal to nh by 2 pi. We are just using this value of r here. Here instead of using r, we are using the value derived from equation 3. Okay, so let's cancel out. M gets cancelled, V gets cancelled, 4 pi gets cancelled with 2. What we are left with? We are left with the value of V, which comes out as Z E square divided by 2 epsilon naught N and H, and this we call as equation number 4. So now we have got two equations. We have got the value of radius and we have got the velocity with which the electron is moving. Okay. Now if we substitute this value of V here, let's say we have got the value of V and we substitute this value of V in equation number 3 here, what we will come up with? We will have the value of R as epsilon naught h square into n square divided by pi m z e square. I hope you guys have understood. If not, I will do it again. Should I? Okay, I'm doing it. From equation 3, what do we have? We have R is equal to z e square divided by 4 pi epsilon naught mv square, and we have the value of V here. What is the value of V? Which is z e square divided by 2 epsilon naught nh. So using the equation 3 and equation 4, what we will get? We will have R is equal to z e square into 4 pi epsilon naught m, and instead of V square we will use this value, and hence we will come up with 4 epsilon square n square h square divided by z square into e to the power 4. Okay, this e to the power 4 gets cancelled with e to the power 2 and we have remainder of e to the power 2. Z square gets cancelled with z and we have 4 gets cancelled. This epsilon gets cancelled with another epsilon, and this is what we have got. So we will have value of R is equal to epsilon naught n square into h square divided by pi m z e square. Okay, so this is how we derived. So we have got the idea. Okay, since we have got the velocity of the electron and we have got the radius of the path, okay, we should know what should be the kinetic energy of the electron. Let's say this is the electron moving. We should know the kinetic energy. Here in quantum mechanics we write kinetic energy as K. So K is half mv square, and we already have the value of mv square. In the first part only we have got the value. What is the value of mv square? Mv square is z square divided by 4 pi epsilon naught into r. So we will write this value here, and we will get half into z e square divided by 4 pi epsilon naught into r, which comes as z square divided by 8 pi epsilon naught into r. Okay, and just now we have found the new value of r, which is this one. So we will use this value of r and we will come up with z e square divided by 4 pi epsilon naught into epsilon naught n square h square pi m z e square. This was the value of r. We are using this value, and hence we will have pi which gets cancelled, and we will have the value of m z square e to the power 4 divided by 8 epsilon naught square n square into h square. So we have two values of k. This is one value where we have used the value of r, and this is another value. K is this 2. Okay, so this is the kinetic energy. Now we would require the potential energy of the atom too. potential energy. Potential energy of the atom would be denoted as V. V is equal to, we know the field theory. Okay, so this is, suppose uh, this is the proton, it has a field, it's acting on this electron. So we will have Z is square 4 pi epsilon naught into R, which will come eventually as Z is square 4 pi epsilon naught, and we will have the value of R. So E square H square N square is equal to pi M Z square, and it will come eventually as minus M Z square e to the power 4 and 4 epsilon naught H square into N square. So this is the value of potential energy. So now we have total energy. So if we write the total energy, it will come around as potential energy plus kinetic energy. We have denoted kinetic energy as K and potential energy as V. And we will come up with the value of M Z square e to the power 4 divided by 8 epsilon naught H square into N square. So this is the total energy. Okay. And this is the total energy of the system. So what do we have now? We have the radius of the electron moving around, revolving around the nucleus. We have total energy, we have kinetic energy and potential energy, as well as we have the velocity. So now for a hydrogen atom, Z is equal to 1. Z is the atomic number. Okay, so we can put the values and get the radius. So radius would be equal to R1, let's call it R1, epsilon naught H square divided by pi M Z square. If Z is equal to 1, then we have all the values here. This is a constant, pi is a constant, mass of the electron is a constant, charge of the electron is a constant, Planck's constant is there. So it will come around as 0.53 angstrom or 53 into 10 to the power minus 12 meter, or you can write it as 53 picometer. So this is the radius of hydrogen atom. Okay, so we generally denote it as A0. Okay, so for a hydrogen atom with Z protons in the nucleus, it would come around as Rn is equal to N square into A naught. Since we have seen that R is proportional to N square, where? Let's go back here. R is proportional to N square. R is proportional to N square. Hence we can write R to be N square into this whole things, these are all constant, into A naught. So this is the whole concept behind it. Getting my point? And for a hydrogen-like atom with Z protons, the nucleus would be Rn into N square into Az into A naught by Z. But we have seen when we try to verify it experimentally, this data fails. The whole postulate of Bohr is only applicable for hydrogen atom. Why? Because this is the simplest model. It has got atomic number of 1. It has only one proton, one electron. So this is the simplest idea, and the structure of hydrogen is been described by Bohr's model. Okay. Now there is a concept we should decipher why the wavelengths were coming of certain values. So we will discuss why these things happen. Okay. So Niels Bohr said that energy of the atom has definite value. Energy of the atom has definite value in a stationary state or stationary orbit. Okay, we have seen, but let's say this is the stationary orbit. Here is the nucleus, and these are the stationary orbits. Okay, so Bohr says if an electron is here, it will have an energy which will be equal throughout. If the electron is here also, it will not radiate any energy, and it will have same energy in a stationary orbit. But if we heat it, we give it heat or give it electricity, it will jump to higher states. Okay, it will absorb the energy and the electron will jump to higher states. And then the electron, since it has got up to the excited state or the higher state, it will come back. When it will come back, it will emit radiation. And this is been described by that old formula, 1 by lambda is equal to r into 1 minus n square by m square. So this was the whole idea. And we will see how this thing happens. Okay, this is the proton. Let's say this is n is equal to 1. This is n is equal to 2. And this is n is equal to 3. Okay, or let's say this is n is equal to infinity. So this one is the nucleus. Okay, it has a radius of r1, it will have a radius of r2, similarly it will have a radius of r3, and let's call this as infinity. So this one will be n is equal to 1, n is equal to 2, and n is equal to 3, and this is n is equal to infinity. So this is how the Bohr's model has been described. Okay, so when electron is there in n is equal to 1, it is its natural position. This is called as ground state. Ground state. And we can derive the formula En is equal to how much? We have the total energy which we derive from this formula. Which formula? This formula. E is equal to minus mz square into e to the power 4 divided by 8 epsilon naught square h square n square. So we can use this same formula. Let's cut it out. Here we have this formula. Okay, perfect. Now for En we have minus m z square e to the power 4 divided 8 epsilon naught square h square into n square. If n is equal to 1, what will be the value? E1 is equal to minus m z square into e to the power 4 divided by 8 epsilon naught square into h square, since n square is equal to 1. Okay, these are all constant. M is the mass of electron, Z is equal to the atomic number, E is the Coulomb's charge, epsilon is a constant, H is equal to Planck's constant, and this way we will come to the value of E1 would come as minus 13.6 electron volt, or you can write it as En is equal to minus 13.6 electron volt by n square, where n is equal to 1. In the same way, let's say we have given it a heat, and as a result the electron has moved from n is equal to 1 to here n is equal to 2. It has reached to an excited state, and since it has reached, it will have to come back again. When it comes back, it emits radiation, and this radiation will be explained by the formula E2 minus E1. Okay, just now we have seen En is proportional to 1 by n square. So here you have found this formula. En is equal to or proportional to 1 by n square. So by this way, if we see E is equal to h nu or E is equal to hc by lambda, so energy is proportional to 1 by lambda. Hence, 1 by lambda is proportional to energy. So if, let's say, the electron is jumping from the excited state of m to the ground state of n, so m minus n, this will denote the wavelength, which will come to be around 1 by lambda is equal to m z square e to the power 4 divided by 8 epsilon naught square h cube by c into 1 minus n square by 1 minus m square. And this thing was written as r, as Rydberg's constant, And here we have found that old formula of why the peculiar wavelengths were coming from the hydrogen atom. Got my point? Now you may ask how we got this value. How we got this value? So we know E is equal to hc by lambda. Hence 1 by lambda would be E by hc. We already had the value of E. We already have the value of E. So let's copy it from here and paste it here. So this was the value of E, which is minus m z square e to the power 4 divided by 8 epsilon naught square h square n square, and here we have two more thing, h by c. So it will come around as what? M z square e to the power 4 8 epsilon naught square h cube n square into c minus, and we are talking about the wavelength, so em minus en. So if we do that, it will come around as m z square e to the power 4 by 8 epsilon naught square h cube n square c by 1 minus n square by 1 minus m square, and this is the Rydberg's constant. So I hope you have understood. We started a discussion, okay, with Thomson's model, then we talked about Rutherford, then we looked at the limitation of Rutherford's model, we looked at photoelectric effect, then we looked at the wave function, why the hydrogen behaves in a peculiar way, why these distinct wavelengths were coming, and a random mathematical formula was derived back then by a school teacher called as, what was his name? I think his name was Balmer. Okay, and we couldn't explain at that time why this weird equation comes, which was further discussed and derived by Bohr's theory of Bohr's postulate and Bohr's model, Bohr's atomic model of hydrogen. Okay, and accordingly we have various series. So let's say this is n is equal to 1, where E1 is equal to minus 13.6 electron volt. Then we have n is equal to 2. Then we have n is equal to 3. And let's call this n is equal to infinity. So accordingly we have various types of spectrums. So from n minus 2, n is equal to 2 to n is equal to 1, from n is equal to 3 to n is equal to 1. So when these things are happen, they are shown as electromagnetic waves, and this gives the spectra which we are discussing. So if it falls to n is equal to 1, these are called as Lyman series. If they fall from infinity t to n is equal to 2 or n is equal to 3 to n is equal to 2, it is called as Balmer series. So like this there are various names. N is equal to 3, it is called as Bastian. So these things are not important. We have looked at the derivation, how this question arises. We have looked how the formula of wavelength comes. So this was the basic gist for today. I think you have understood it. Thank you.